Thank you very much for introduction. Thank you very much for invitation. You know, it's always a pleasure for me to be here. And I think the number of times I came here is something like uncountable. In any case, I cannot count them. Although possibly it should be finite. There should be some proof that it is finite. But okay, so thank you very much to IMSC, and thank you very much to Shaoli, who is always brilliantly organizing everything here. Okay. So this first introduction to the course, which is an introduction to probabilistic number theory, is something which is a bit just to give you some idea of what we are going to do about. And possibly a first thing to do in this introduction to introduction, this chapter 0, is to understand what are the connection between probability and number theory. So it will occur in the following way. There are essentially four themes, which are probability leads to models for the integers. Is one thing. Now the other thing is that if you are using probability techniques, first of all, probability techniques may give you, may help you to prove number theoretic question. So proba helps, permit to prove number theoretic question. This is another thing we are going to see. And also another thing which is interesting, we'll look at that rather close to the end of the question, is that number theoretic question, it goes the other way around. It's not always proba that gives something to number theory, but number theory may bring something to probability. And there are two aspects. One aspect is that number theory questions indeed lead to probability questions. This we'll see some example, and something we are possibly not going to see except maybe today, but I don't know whether we have time enough to do that. Otherwise it will be on Friday, that I'll explain that on Friday afternoon, maybe give some example that indeed number theory questions, number theory permits to prove probability questions. Okay. So we keep that in mind, and when we give some example, we understand how it goes. Okay. So now let us enter the business and go to the first part, which is multiplicative questions. So indeed, this is connected with the root of probabilistic number theory. Probabilistic number theory is essentially considered as having been introduced in 1917 by Hardy and Ramanujan. This is so about 1 century ago, the probabilistic number theory has been introduced. And then it has been much developed in the 50s by Paul Erdős. And what they prove is the following, the theorem is the following. Do I have room here? Yeah, it would be good because then I can leave it here. So the theorem of Hardy and Ramanujan of 1977 says the following. Okay, let psi of n increasing and tending to infinity. Okay, so there's just any function like that. What is interesting is that you want to count the number of n up to capital N, for which, if you look at the number of prime factors of n, That is to say, p divides n. This is the number of prime factors of n. Essentially, this is something like log n. We'll see why it is something like log n, but I tell it to you, so it is log n. So log is just the Neperian logarithm that you are, I guess, supposed to write as little l and n as the international norm, but for mathematicians, usually we still use this log. So this is just the Neperian logarithm, log n. And so that this is at most psi of n square root of log n. So what they say that if you consider the integer up to n for which this is, this is less than psi of n log n, essentially this is almost all the integers. You see, when I say almost all, I have already some probabilistic flavor in that. What we mean by almost all, it means that this is supposed to tend to 1 when n is tending to infinity. And of course, this is not true, but I take the frequency. So what we do is the following. What we are saying is essentially that if you take the integers such that the number of prime factors, counted without multiplicity, but it will be the same thing if you count them with multiplicity. Count them without multiplicity is log n. Essentially, this is almost all integer. Take a sort of random integer around capital N, then its number of prime factors will be log n. You understand that in this, log n is an almost constant function, which means that here you can easily replace the little n by a capital N. It will not change much. Okay? Okay, so this is the thing. And now I would like to give you an idea of the proof. And the proof is not the proof that was given by Hardy and Ramanujan. The proof by Hardy and Ramanujan used indeed the number of integer up to n which have exactly k prime factors. So if k is equal to 1, it is the prime number theorem, and then they were building on that to say something about the number of integer up to n having exactly k prime factor. But the proof I am going to give is the proof which is due to Turan, Paul Turan, a Hungarian mathematician, and his proof was given in 1934. And give it to them. So what it does is, first of all, you give a name to this. You call little omega of n is summation when p divides n of 1. Okay, so this is the number of prime factors counted without multiplicity. I think up to now it should be more or less okay, but I wanted to tell you if there is something you want to interrupt me, do not hesitate to interrupt me. Then your picture will be taken for eternity, if it is not lost. Okay, so fine. Now what you do is the following. You count the number of, you look at the mean value in some way of this function. You see it is a sort of mean value. It is exactly the, you take each of this value with a weight which is 1 over n, up to capital N, up to 1 over capital N, and you see what you get. Well, this is not too difficult. This is a very nice situation because what we are doing is summing. We have a double sum. And this is wonderful because you know what you do when you have a double sum, you just reverse summation, as you do usually. Okay, and so this will be the sum. Should I do it here? Okay. So now when you reverse the sum, you will say that this is, you are counting, summing on p. Since p divides n and n is at most capital N, just consider the p which are less than capital N. The other one have no interest. And then you are reversing that. So now what you are doing is you are counting. So you have the n minus 1 still exist. And then you are counting the integers up to n, which are divisible by p. We have to keep the same thing. But the number of elements up to n, integer up to n, which are divisible by p, you know exactly how many they are. They are exactly n divided by p. Okay? So now you know what you are doing, and what you are doing is to say that this will be, you break the, maybe now you maybe write it like that. The floor function. You know the floor function for a real number. You write always a real number x as this plus its fractional part, and this belongs to z, and this belongs, the fractional part belongs to 0, 1. Okay? There's a unique way to write an integer that way. So this is the. So this means that this number is essentially x plus something which is bounded. Big O of 1, even with a constant, you master completely. So, okay, what it means? It tells you the following, that you have n minus 1. If you take just the part n over p, n disappear, and you are summing p up to capital N. Okay, summing p up to capital N, this is something which is rather basic. It's weaker than the prime number theorem. It's due to Mertens. And so this was known in the 19th century, that the summation of the 1 over p, p up to n, is something like log n. Essentially, it is more or less due to Euler. The Euler proof of the prime number theorem tells you that the sum of the inverse of the primes up to n is something like log n. This is this way to prove that there are infinitely many primes. So this is something which is log n, so we are quite happy. This is what we expect. This is log n. And now what you have for the number, if you have a 1, then it is the number of prime up to n, which is something like n over log n. You don't need to have the prime number theorem for that. Chebyshev, beginning of the 19th century, it's quite enough to say that this is little o of 1 in any case. Okay, so this is plus little o, no, plus big O of 1. Okay. Okay, yeah, because little of 1 in the terms which is the Euler term, but also for the sum of the inverse of the prime, you have a constant here. And Mertens tells you exactly what is the constant, and all that is quite basic things. Okay, so this is the first step. Now the second step is to do the same thing. I'm not going to do it today, but to say something about the square. Slightly more complicated, but not too much complicated. We'll look at that tomorrow morning. And then you say the following, that this turns out to be log n square plus big O of log n. So you just believe me, this is some little work in number theory. You see that in Hardy and Wright, or whatever is your favorite book for number theory. Good. Now what you do is the following. You are counting the number of n up to capital N for which this is false. That is to say, for which this is larger than that. Now what Turan is doing is saying the following. The number of n up to n for which, so you want it to be false. That is to say that what you are writing is omega of n minus log n. As I told you, this is the same thing to take a little n or a capital N. You can shift it if you are considering element up to capital N. Essentially, this function is constant log n. This is not a problem. It's larger than psi square of n log n. You can put a little n or again a little n or capital N. This is the same thing. So what can you say about that? Is at most, what you want to say that the number of n for which this is false is a little o of n. Okay? This is the same thing as saying that the number of n for which it is true tends to 1, the proportion tends to 1. It is just to say that this number is little o of n. So how can we get the fact that it is little o of n? So, and then here is the trick, is to say it is at most the following. Sum n up to n of omega n minus log n square divided by psi of n square log n. If I have this, which is larger than that, I say that this number is at most that. So why is it true? You have two categories of n. You have some n for which this is true. If this is true, it means that the quotient is larger than 1. So if I want to count them, I just take an upper bound. Instead of counting 1, I count this number. This is fine. And there are the other ones. The other ones, they are not counted at all. Okay, put any positive weight and you are happy. And this is a positive weight. Okay? So this is an upper bound. And now you are happy with that because you know everything. What can you say about that? Well, omega of n minus log n, you have everything to expand it. It will be, when you square it, it will be log n square. And then you will have the double product, which will give you something which will be, again, the log n square 2 times. So up to now, we have something which is a minus log n square. And then you are going to put, again, this log n square again. And so you will get something which will be, at most, something which will be 1. And so it is n divided by psi square of n log n. No, psi square of n. Full stop. Okay? So this you get just by expanding this and taking the fact that the main term will disappear. You see, when you square this, you get a log n square. When you square it, you get a log n square. And when you take the double product, you gain again this double square. So the log n square disappear. You have just something which is a log n divided by log n. It is a constant, and you have the y 1 over psi of n.
Small n down, so will there be some property of psi function?
Yeah, psi is a nice function. Okay, not going too quickly. Okay, let us say if you want to know what they were doing is take psi of n, which is indeed in their proof. What they obtain is something which is log n to the epsilon. Okay. And then you have this. I agree with you that I was putting the extreme value, but since it tends towards infinity, there may be the, okay. But if you do that, this is fine because you know that log n is almost a constant function, and so this is a constant function. Good. So this is the proof of Turan. Okay. Good. Now we want to understand where it comes from. So if you know some, interesting. Are there people who have never seen anything about probability here? No, essentially you know something about probability. So one of the tools you have in probability, you may figure out here. Maybe you have seen some trick like that. No? Okay, let us see the proof. What is the idea behind the proof of Turan? Okay, behind the proof of Turan is the following. Okay, so what he does is the following: is introducing a family of random variable. So consider a family of random variable, Bernoulli random variable. Bernoulli random variable means simply that it takes value only 0 and 1. Okay? Bernoulli random variables, so with value 1, which are independent. I don't know if we need it, maybe not even. Yes, we need it. Let us say independent. We'll see why it is better to say independent. Such that the probability that, so I didn't give the name, the family, there will be xp for prime p, such that the probability that xp is equal to 1 is 1 over p. Why? What is he doing by that? He's saying the following, that indeed, if you have an integer which is divisible by p, in some ways a sort of heuristic probability that an integer is divisible by p is 1 over p. If you go up to, it's not exactly a probability, we'll see the difficulty with that, but this is why it makes life difficult. Otherwise it would be just trivial, it would just be probability, and we wouldn't speak at all about number theory.
Identically distributed also, or only?
Sorry?
So those are also identically distributed? Those XPs are also identically distributed?
No. You see, they are not identically distributed because this probability depends on p. So more or less it will tell you that an integer is divisible by p. This occurs with a probability which is 1 over p. Okay? So it's different. To be divisible by 2, essentially it is 1/2 of the time, but to be divisible by 19 is much less often. Okay, so they are not at all identically distributed. The law depends on that. Of course, I don't say what is the probability that xp is equal to 0. It is 1 minus 1 over p, because you just take two values. Okay, so you know what it is. Good. Okay, and now what he does is he introduces something which is let us say omega tilde n, which is the sum of the xp p up to n. Okay, so this is in some way, usually it will say that if you draw those family, it will tell you more or less how many times something is, how many prime factors you have. You see, the expectation will be just what you have. You take an integer, you say how many times it is divisible by 2 about half of the time, how many times it is divisible by 3 about 1/3 of the time, how many times it is divisible by 6, it is about 1/6, and so on. Okay. So now what you do with this is, so this is a random variable, which is the sum of a finite number of random variables. There is no problem. We let that n tend to infinity later on. So for the time being, what we are doing is we try to know, so this is the first step. In some way, this is what is here. Instead of saying we are summing 1 when p divides n, we are summing this random variable, and the probability, if you take an integer n, some sort of random variable, how many times will it be divisible by 2, 3, and so on, is given by this xp. So this is definitely the probabilistic model. We're exactly here. It's to a models for integer. This is the model we have for integers. This will be quite often we are going to introduce things like that. So of course what you try to do then is to compute what is the expectation of omega n tilde. Well, expectation of a sum of random variable, this is not too complicated to compute because the expectation is just linear. So it is the sum of the expectation, and if you have a Bernoulli random variable, you know what is the expectation. It is 1 times the probability that it takes the value 1 plus 0 times the probability that it takes the value 0. And so the expectation of this random variable is 1 over p. And so the expectation of that is simply the sum when p is up to n of 1 over p. Okay? Good. So you need, at least here, you need some number theory to know that this is indeed log n plus big O of 1. Okay? So we need, but this way we give the complete proof of that. We don't need something sophisticated here. So okay, we know what it is. This is log n plus big O of 1. Okay? Now we try to get something about the variance, dispersion, which is the same thing more or less than the mean square. So here we were looking at the mean square. In probabilities, maybe better to look at the variance. So you look at what is the variance of omega n tilde. Variance of omega n tilde. This is not too complicated to look at the variance because where suppose that they are independent. And independent corresponds to something if you are being divisible by prime factors, because if you say it is divisible by 2, okay, you have about 1/2 of the element, but divisible by 3, it's about 1/3, but being divisible by 6 is 1/6. So in some way, the heuristic probability is the product of this probability. So it is in some way independent events to be divisible by 2 and to be divisible by 3. So this is basic observation. This is all the multiplicative questions will play on that in the model being divisible by 2 or being divisible by 3 are independent events. It wouldn't be true if you said divisible by 2 and divisible by 4. Okay? But this is a good model. So important to understand that this is justified in some way by the heuristic to say in our model it makes sense. It wouldn't make sense to say for any integer being divisible by d and be divisible by d prime are independent events. This doesn't work. Okay? So with prime it's okay. Now since they are independent, the variance is easy. It is the sum of the variance. Okay? So the sum of the variance is summation p up to n of 1 over p, 1 minus 1 over p. This is the variance of a Bernoulli random variable. This is not too difficult to get. And you understand immediately what you get, that here, you see here I told you, okay, the proof I'll give you tomorrow. Here, the proof I'll give you immediately. Because you have summing 1 over p, you know what it is log log n, plus big O of 1. But summing 1 over p square, well, 1 over p square is a convergent series. So it is big O of 1. I mean, convergent, it has nothing to do with prime numbers. Just take an upper bound with all the integers. The sum of the inverse of the squares is something which is convergent. So this part is easy here. Okay? Now what you do, of course, if you know those two things, what we are saying about taking this, which is the difference minus the, will be about the same thing. Now what you do is to say, aha, but if I know something about the expectation and something about the variance, then there is a nice tool which is called, and you want to get that, and even I give you the proof, you want to go to that, what do you use to get something like that? This is called Chebyshev or Chebyshev bien-aimé. Okay? This is Chebyshev. So now use Chebyshev. Okay? Use Chebyshev inequality. Chebyshev inequality tells you the following, that the probability that omega of n tilde, this is a random variable, minus expectation, you take it centralized or whatever you call that, the probability that this is at most u times, or let us say psi, I use just a number psi times it's not exactly the variance you are looking at, it is the square root of the variance, which is very good, which is called the standard deviation. This probability, no, it goes the other way around. This probability is at most 1 over psi square. This is exactly Chebyshev inequality. And if you don't remember what is the proof of Chebyshev inequality, this is exactly the proof of Chebyshev inequality. We'll have opportunity to go back to that if needed. Okay? So indeed, you have seen, so this is in the model, and now if you copy the model in the real life, you have something like that. So it tells you also that in some way, it's not exactly permits to prove number theoretic question, but it gives you some inspiration how you can prove it. And you really see when you see this, that this is good inspiration, and this was indeed the inspiration for Turan. You see, whereas the proof of Arden Ramanujan is not really probabilistic proof. But this in essence, it is probabilistic proof. So now there is something which is very important to keep in mind here, is that you have in some way the real life, and you have something which is the model. Okay. In the model, there is one thing which is easy. In the real life, there is something which is complicated. Well, this is not awfully complicated, but it's a bit more. Try before tomorrow to prove that, and you'll see that if you don't take it cleverly, you may turn around. It may be a bit clumsy to do that. So in the real life, you have a problem with the variance. In the probabilistic life, you have no problem with the variance. This is very easy. Okay? So this is to introduce something which will be in the first part, which in some way will culminate, and then there will be application of that, which what he calls the Turan-Kubilius inequality. Turan-Kubilius inequality will tell you that this is for a lot of function which are, this is an additive function in the way that it is the sum of a prime divising n of something. Additive function will be something which will be f of n is the summation when p divides n of f of p, at least what is called strongly additive function. So you see that you can do something which is more or less like that for any function f. Now if you have a function f which is not that easy to look at, it may be difficult to get something like that. Usually the mean value is easy, you just interchange two summations. You see this function is a sum, so just interchanging summation is fine. Getting something about the variance may be difficult, where in the model it's easy. And Turan-Kubilius tells you, well, build a model. Of course, the situation will not be that xp is equal to 1, but xp is equal to f of p is 1 over p. And you can do something of the same kind. And the Turan-Kubilius inequality will tell you that the real life is never much worse than what you have in the probabilistic model. But in the probabilistic model, it's much easier. So once you have this tool, which is Turan-Kubilius inequality, you are very happy. You don't have to worry about the variance in the real life. Turan-Kubilius is telling you the variance in the real life cannot be really worse than the variance in the probabilistic model. Okay, and in the probabilistic model, it's easy to get. Of course, you have to work a bit to get this, but you do the job only once. And then you have Turan-Kubilius and you are very happy. Okay? So in some way, this is where then you use probability to compute the variance and something like that, and this is where this permits you to prove number theoretic questions. Okay. So let us move a bit forward. Maybe I give you, since it is just a general thing, let me give you the Turan-Kubilius inequality. Let me write it instead of just waving hands. So, okay. This is not at all what I'm going to say. This is here. Okay. Yeah, before doing that, I want to tell you something more. So, okay, let us say that this was the proof of the Hardy, let us say 2-1. This is the proof of the Hardy-Ramanujan inequality. Now you can do a bit further. Okay, this is a sum of random variable, independent random variable, which are bounded, and you have something which tells you that you know indeed much more on what is the behavior, asymptotic behavior of that. And the asymptotic behavior is something which is called the central limit theorem. So central limit theorem tells you the following, that you have bounded independent random variables. Usually it is proved the easiest thing in when all your variables are equidistributed, but you have a lot of different ways to do that. And indeed, even the central limit theorem, here you have happy because you have a variance and a bounded function, so it's not too difficult to get that. And we'll tell you the following, that the probability that omega n tilde minus e of omega n tilde is less than u times sigma of omega n tilde. It is more precise than that. It tells you something that this probability, when n tends to infinity, you know exactly what is the limit. You see, here is this to say that if you are far apart from the central value, from the expectation, from the mean value, if you are far apart, you don't have too many people. Here it tells you exactly if you are, so you just normalize that, and what is this? And this, you know exactly what it is. This tends to 1 over square root of 2 pi integration from minus infinity to u of e to minus t square over 2 dt. Okay? So it tells you in some way that if you are summing independent random variable and you are doing something, of course, which is just some normalization. Normalization is take out the expectation and divide by the central deviation, by the standard deviation, then you get something which follows the normal law, Gaussian law. Okay? Good. Let us say this is phi of u if we need it. This is the central limit theorem. Okay, then now when you know the central limit theorem, you say, aha, but let us go to real life. Do we have something like that in the real life? Yeah, and the answer is yes. And this is due to Erdős and Katz, 1940. Then it goes a bit forward, you see, into the probability. It tells you, yes, this is true also for the real function omega of n. Okay? Erdős, Katz. So it will tell you the following, that for any u, we have the following: 1 over n, the cardinality of n up to capital N, such that omega of n minus log n, little or large, it is the same thing, smaller than log n. You recognize what is the mean value and what is the standard deviation. We computed that. This tends to phi of u when n tends to infinity. Okay, and it's not by chance you have that you see Erdős and Katz. It was, I think, at the end of a lecture of one of the guys. I think it was at the end of the lecture of Erdős that Katz says, but we should be able to prove that, and so they just sat and proved this. Okay, so for any real u, you have this, and this is the Erdős-Katz theorem. And I was announcing it, but it turns out that I don't think I have time in this short time to present that. It's rather technical to prove it, so it's better that you have it in mind now.
Maybe in the next week.
Hmm?
Maybe in the next week.
Yeah, maybe in the next time, yeah. Or maybe we'll do something else. We'll see. Okay, but we will see at the end. If there are things you want me to go into more details, we can do into more details like that. But there will be a lot of material, so maybe this is not the most important. By the way, you see, the point is that very often you go when you have problems like that. It's not really problems in number theory. It's not really problem in probability, but you have a lot of questions in calculus and analysis and okay, so I'll be a bit waving hands on certain matter. I will give you a proof of the Turan-Kubilius inequality that I'm going to quote now. So now we go to, in some way, want to generalize that to additive arithmetic function. So what is that? Additive arithmetic function. what we call arithmetic function, as you possibly know if you have studied a bit number theory, it's just a sequence of complex numbers. This is what we call an arithmetic function. Of course, we're just considering some which have some special property of interest for number theory, but if you want to give really what does it mean, arithmetic function is just a sequence of complex numbers. So the one which will be of interest, I already told you what we were going to do. Is the following. So what it is, you have a function f, which is from n to c. And we're interested in function which is additive. So this is arithmetic function. And we said additive, which is multiplicative. When you have the following, that f of m plus f of n m is equal to f of m plus f of n whenever if mn are co-prime. GCD of mn is equal to 1. Remember GCD, I just write it as mn, thinking maybe of the ideal generated by m and n. Okay, and the multiplicative will be the same thing, except that here you have a multiplication. So this has nothing to do with what we are going, when we are talking about multiplicative questions. I'm thinking of additive functions or multiplicative functions. This is definitely the multiplicative structure of the integers which is behind. You see, which is to say that it's f of mn is this. When I'm going to talk about additive question, it will be something different. For example, sum of 2 squares, sum of 2 cubes, sum of 3 cubes, and so on. Okay? Good. So this is what we say, and this additive function. And essentially, additive function, it is enough to know it on the prime powers. Of course, you have if f is additive, and I am not going to talk about multiplicative function. By the way, if your function have value which are, let us say, positive real, then it is the same thing. You just go from the exponential or the logarithm, and you go from one to the other. So it's essentially the same thing. Okay, and then if it is additive, you have f of n, which is just the sum when p to the alpha divides exactly n of f of p to the alpha. Okay, so to make our life a bit easier, I'm considering something which is like the little omega of n function. Little omega of n, that is to say, counting the prime factor without multiplicity, I assume that f of p of the alpha is independent of alpha. You see, if I say an integer is divisible, the number of prime factor without multiplicity, I don't care if it is divided by p squared. I say, okay, it is divisible by p once, and that's it. So this is what we call strongly additive. Strongly additive will be that this is the sum when p divides n of f of p. That is to say, p of p to the alpha is equal to f of p to the alpha is equal to f of p regardless of alpha. It makes our life a bit easier to write it down, but it's not a big restriction. P divisible by square, you don't have that many elements, you see. Then you have the sum of the inverse of the square is something which is convergent. So it may pollute a bit your life, but fundamentally it doesn't change the matter. So it makes sense to look only at strongly additive function if we want to go a bit further. Blah, 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 blah. So we have the same probabilistic model. So probabilistic model. Probabilistic model tells you the following, that xp takes the value f of p, or take the value 0 with a probability, again, so xp, p belongs to p, are independent Bernoulli random variable. And what you expect for this probability to be 1 over p. This doesn't change. Being divisible by p is that, except that you are going to sum Instead of summing 1, as we were doing before, for counting the number of prime, we're just counting something which is f of p each time. Okay? So this is the model, in some way, this is the probabilistic model for f of n, which is strongly additive. Okay? So you know what it is. And so if you consider summation when p is less than n of xp, this is a probabilistic model for f of n when n is around p, when n is around capital N. Good. So now what we would like to do, I think you can, yeah, this we have because we have more than that. We have even Erdős-Katz and something other kind. Okay. So what is the question? The question is compare, this is what we are doing, 1 over n, cardinality of n up to n for which f of n, let us say, is less than u. Let's call it directly u. And the probability that the sum when p is up to capital N, or up to, yeah, capital N, of xp is less than u. This is the real life. This is the probabilistic model. And you would like to compare those two things. So we assume here, when you write something like that, that f is a real function. When f is strongly additive and real. Okay, it doesn't work exactly like that. There is a problem that if you are considering very large primes, then you may get into trouble. They don't occur that often. You may have difficulty with that. Now, something which would be trivial is just consider only very, very small primes. If you consider very, very small primes, you can do everything. You have good error term from everything. You are very happy with that. But this is really too weak, because you would have, if you want to consider, to break this and to consider only primes which are very small, then it should be something like log n or something like that, like in the Legendre sieve. You see, how can you count the number of elements up to x which have no prime factors? Well, we can do that only up to log x. You see, the Legendre sieve is not that great, but we have better tools which say that essentially you can go almost up to a power of n. So this is sophisticated sieve. It is what is called the fundamental lemma by Brun. So it is Brun's sieve and fundamental lemma. I'm not going to enter that, but I'm going to tell you what it means and what is the output of that. I'm not going to prove that. Maybe something like sieve could be a better theme for a next course than going on with something like that. So thanks to sieve, you have what is called the Kubilius model. Kubilius model tells you the following. So we are going to cut it at a certain power of n. Okay, we cut at a power of n, and this power of n has just the only interest is that v is small, simply tending to 0. We don't ask for more than v tending to 0, but we just keep all the prime factors up to n to the r. This is what we are doing. So the Kubilius model then tells you that you can compare 1 over n, cardinality of n up to capital N, such that the sum of f of p You need to have some condition on f, but rather mild. This so you are truncating your function. You are truncating at r, which is a little power of n. Okay? So large prime factors, leave them out, but usually large prime factor you don't have many. Think, for example, of the omega function. Omega of n, you say, okay, consider that v small is v is 1000. Okay. So you are saying, oh, I am just looking at the prime factor up to n to 1 over 1000. Well, but you are not losing much, because how many prime factors larger than that you may have? At most 1000. 999 if you prefer, but at least you have at most 1000 prime factors. And what is 1000 compared to log log n? Peanut, if n is large enough. Okay? But so it means that this is not real restriction, you see, to have something up to a power of n. You maybe let out large prime factors, but there are not many prime factors. They don't play a large role. So this will be very useful. What I'm going to say now, that this minus the probability that the sum xp, xp, when p is at most r, is less than x, this I can compare. And this I can compare, and this is a big O of, this is not the best that can be done now, but it is something like that, which is very nice. N to minus 15. It's okay, you don't care. This is about constant, you see, both sides. Something I can consider. This is little of 1. So this is fine. Plus some term which is exponential of log of v divided by 8v. Okay. This is what is the life. Okay? So v is small. So this is negative, which is good, exponential of something negative, it's smaller than 1, and this is tending, if v is small enough, this doesn't play a large role, because this is negative, but will be very large. Because you see, it is essentially, forget about this log, it is 1 over v. And v is very small, so this is exponential minus something which is large. Okay, so this is a good inequality. Okay. So this is what we call the model, Kubilius model, tells you that this is fine. So for example, once you have something like Kubilius model, but as I tell you, it is non-trivial, it depends on sieve methods. So in some way you have something which is hard on the number theory side. But when you have this, then now this, I don't have any longer Erdős-Katz. But you understand now what it is, because it tells you that Erdős-Katz in somewhere on the probability side, it's known, it is the central limit theorem, but on the real life it is Erdős-Katz, but you have this correspondence except that you have to truncate as something which is, okay, n to 1 over 1000. Okay? But then if you want to count the number of primes which are larger, there are not that many. So from this, once you have this Kubilius model, for example, Erdős-Katz, you will get it immediately for free. It tells you, okay, I forget about a certain number of primes, but there are not that many, and outside this number, the real life is exactly like the probabilistic life. Okay? Sorry?
This part is almost equal log n by log n, right?
Which part?
This exponent part?
This exponent part? Well, it depends how far you go with v. You see? It depends. As long as v is a constant, then this will be a constant. But this constant is a constant will be smaller and smaller when v is smaller and smaller. Okay? So you just have to play a game with that. I mean, this is the classical thing with epsilon. Consider that if you want this to be very small, you don't have to go that far. This goes very quickly to 0 when v tends to 0.
So here is 15 something special or just a number? Nth power minus 1 over 15 is just coming?
No, this is coming really, this is really coming from the sieve. No, this is not, you cannot replace this minus 1 over 15 by anything. Well, you have to work a bit more, but there is something like that, which is already quite good. Usually you don't have something which is as good as that, but it's winning already a power. You see, we are winning a power of n, and usually what you will do here is just try to find v as you can to get something which is a little of 1. Okay? This just to tell you that this part is usually nothing. What is important that this is a little of 1 as soon as v is a little of 1. And usually when you are, what I was telling you is that the large prime factors, you can deal with them just very easily. So Erdős-Katz, getting Erdős-Katz out of that is just almost trivial. You simply have to know what is going on here. What is going on here is the central limit theorem. Okay, this is probability. Then you see probability permits to prove number theoretic question. You know central limit theorem. Now here you know something which is forget about the large prime factors, but you know there are not that many prime factors. In an integer there cannot be, the contribution to little omega of the large prime factors is nothing. It's p naught. So this you get easily, you get the approximation, and now you get exactly that, and this is what you wish. So in some way getting Erdős-Katz from that is quite easy. Good. I see the time going rather quickly, and okay. Do I tell you about Turan-Kubilius? Maybe not. Maybe not. I don't tell you about Turan-Kubilius because Turan-Kubilius we will have time to work on it. But essentially, I repeat simply that Turan-Kubilius tells you that the variance in the real life is not really worse than the variance in the probabilistic model. And variance in the probabilistic model is easy to get. So it is very good. It means that the proof in some way of summation of the omega of n square, you don't have to do it. Once you have worked on Turan-Kubilius, you can do it in a very general way. Now, you have something to understand, however, is the following, that what is the big difference between Hardy and Ramanujan and Erdős-Katz for omega of n? And this I want to comment because this is something important. Hardy and Ramanujan tell you the following, that the sum 1 over n, the number of n up to capital N for which, let us say, absolute value of omega of n minus log n is less than something which is the square root of log n. Psi at the square root of log n is larger, is at most 1 over psi square. Square root of log n. No, 1 over phi square. Okay. Yeah. Big O. Constant. Okay. Good. Now, there is something which is important here, is that I was saying a priori arithmetic function may take complex values. Now, you understand that when you are doing something like that and looking at such an inequality in the distribution, you definitely need to have real valued functions. So for real valued function, you have something like Erdős-Katz, you have something like the Kubilius model. You need the function to be real to have something which is its distribution. Here, well, expectation is something which can be done easily, and you simply have to add something which is a sort of variance, and usually you don't consider that when you are doing probability, which is Chebyshev in the case of complex random variables. But in the case of complex variable, Chebyshev means sense. We'll have to work a bit at that. Maybe not tomorrow morning, but the day after tomorrow in the morning, we'll look at what it gives. What is Chebyshev in the case of complex valued random variables? But if you want something like the central limit theorem, you definitely need something to be real valued. If you are complex valued and you want to say, because you are saying something which is very delicate, here you get just to say, okay, if I am far from the central value is okay. If you have something which is complex random variable, you know what is the expectation. You see, for any vectorial random variables, you know what is the expectation. So to say it's not too far from the central value means sense, because you are in R to the D, and if it is complex number, you can see then that means in R2, this is okay. But if you want to know very delicately what is the proportion of the elements which are in a given interval, you understand that if you are in R2 or if you are in C, it's something which is completely different. Okay? So we are looking at that. This can be extended to complex valued random variables. For this, you really need to have real valued arithmetical function. It's not the same thing to look at the complex random variable and to look at the real part and the imaginary part. Okay, because you don't know how they are correlated. Okay, so I stop here for that, and I have just some time to tell you about additive number theory now. Because for the time being, we have seen something like that and something like that. We have not seen that, the C part. C part will be for the third part, which is additive number theory. So maybe the best example is a question of Sidon. Sidon was working in harmonic analysis, but his question was the following, and this is motivated by harmonic analysis. Somewhere I'm not have time to go to that, but this is here, that number theory permits to prove probability question. And this is why he wanted to know something in harmonic analysis. So what is the question of Sidon? Is the following. Does there exist a sequence A in N? N is whatever you wish. I mean, the Bourbaki or the AMS1. You put 0, you don't put 0 in this context, it has not real importance. Such that for any n, let us say larger than 1, and so you are happy, there exist A and B in A such that n is equal to A plus B. So what we want to have is a sequence which is such that any integer, any positive integer, or sufficiently large, it will be the same thing because you just complete with a finite set and it will not change much. Is it possible to find a set which is such that n is a sum of 2? Up to now, this is fine. I mean, there is no problem to say that you can find sets for which you have that. This is called a basis of order 2. Additive basis of order 2. Every element is the sum of 2 squares. Every element is the sum of, any element is the sum of 2 elements of A, for example. Order 4, you know that every integer is the sum of 4 squares, Lagrange theorem, and so on. Okay, and what you want is that this to be economic. So that is to say that you want to say that the number of A such that n minus A belongs to A, for given A, So you know that this is always possible to find this term is non-zero. This is to say that this is a basis of order 2. You know this number is always at least 1. So this is okay. This is given by the first term. But you would like it to be economical. That is to say you want it not to be too large. You want it to be little o or big O. This is the same thing for n to epsilon for any epsilon. So this is the question of Sidon. He wanted to have something which is an economical basis of order 2. Economical in the sense that for every n, the number of representation is not too large. If you want to have, on average, the number of representation which is not too large, this is not too difficult to prove. Castle has made very nice construction for that. But can you have that? In some way, for the time being, we don't have any constructive proof of something like that. So now what is the result? I want to mention the theorem which is due to Erdős in 1954. He proved the following, that there exists a sequence A, n, such that when you look at this number, A up to A, n minus A belongs to A. Okay, this is always larger than log n. Maybe even say that there exists C1 and C2. Positive number, the sequence A, such that, so this means, of course, that it is a basis. You are happy. This is for n larger than 2, let us say, for any n larger than 2. True also, by the way, it's true also for n is equal to 1, because this is trivial. Okay. And, yeah, but the upper bound will not be true, so okay. For any n larger than 2. And what is interesting is that now you have to get something like that in the upper bound. Yeah. What is this? So although we have no idea how to construct a set for which we have something like that with n to epsilon, you can prove that there exists a for which you have this. So what is the proof of Erdős? We'll give it. We'll give the proof of Erdős in the course because it's very nice. So what is the proof? Well, I'm not going to give you all the proof, but to say the following. The proof is the following. Define a nice measure on the set of sequences, integral sequences, such that this is true for all sequences, almost all sequences. If it is true for almost all sequences, there exists a sequence for which it's true. Okay? So it's very nice. So what you have to do is to say, okay, what do you want? You want something which is more or less like squares. Because you see, if you are thinking of squares, the number of square up to x is something like square root of x. So the number of representation on average of an integer will be something which is about constant. You see, the total number of representation will be something which is square root of x square, which is x. And with that, we represent integer up to x. And so, on average, it is constant. So what you want to do is just to have a sequence which is a bit richer than the squares. Okay. So now what we do is the following. We say, okay, we are going to mimic the squares. What is to mimic the squares? And then we'll do something a bit different than that. But first, think of mimicking. Does it make sense? How do you write that? Comes that way? It's fine? Of mimicking the squares. This was then developed in 1960 by Erdős and Rényi. Again, you see combination of Erdős and some guy in probability theory. First, think of mimicking the squares. So what it is, you see the difference between two consecutive squares is something like that. If you take an integer which is x to 1/2 plus 1 square minus x to 1/2 square. So this is the average distance between two consecutive integers which are squares around x. Okay, and then this should be something like what? It is 2 times x2 minus 1/2, x to 1/2. About. You factor out x to 1/2, which is x, and then you develop 1 plus x to minus 1/2, and you get something which is that, and you to x minus 1/2, and you multiply by 2, and you get something like that. So that is to say that if you are around x, the probability, heuristic probability to find a square is something like 1/2 square root of x. Okay, this is the heuristic probability. That an integer and around x is a square is something like 1 divided by 2 x to 1/2. Okay? So to get something like a random sequence, you will say, okay, what I'm going to pick up is with this probability an element which is around x. So this will give you something like a square. So in some way you have a probabilistic model for square, probabilist model for square. The following, you take a sequence xn, n larger than 1, such that again, Bernoulli random variable, either, which will tell you in some way, if xn is equal to 1, it tells you that n is in your sequence. If xn is equal to 0, you say n is not in my sequence. So you consider this set of Bernoulli random variables to be the same thing as the indicator function of your set. Okay? And so what you want to say that if I have something which is n, one that the probability that it is in my set is something like 1 divided by 2 square root of n. So which are independent, Bernoulli as usual, such that the probability that xn is equal to 1 is equal to 1 divided by 2 n to 1/2. Okay. So this is fine, you have something like squares, but for that you cannot expect, we look at this model and see what are the sum of two elements in that set. But you cannot expect to cover everybody. You need to put a bit more people about that. Okay? So the construction, so this is just mimicking the square. Now we want to have a sequence which is a bit richer than that. So what we do is the following. What Erdős is doing is the following. So construction of Erdős. Construction of Erdős is the following. You say that let us say let yn, let us change the notation, be Bernoulli independent random variable with probability that yn is equal to 1 is just a bit larger than that. Okay? Is something like, so the constant 2 you don't care because it will be something a bit larger. So you just want something to be a bit larger, and the best you can do is something which is c times log n divided by n. And what Erdős proved is that if C is sufficiently large, this will come from the proof. C is larger than something. You don't care about the value. C is larger than some C0. It will come from the proof itself. It's not complicated. Then under this condition, what he proves is that for almost surely, the sequence you construct that way, so let us say, you may wonder what I mean by that. So, okay. So, I have my, you see, what we have is that you have a large probability space somewhere, and then you have the yn, which are just random variable, that is to say they are functions of your space, probability space to 0, 1. Okay. So what Erdős proves is the following, that for almost all omega, except on a set of measures 0, probability 0, for almost all omega, you have the following, that when you are looking at the set of those n's such that omega n of omega, yn of omega is equal to 1. So this is a set, this is what we call a random set. For each omega, you associate a set, which is the set, in some way you are considering yn to be the indicator function of the function A, of the set A. Okay? So what it proves is that if you look at this set, it has the property, is an admissible set for Sidon problem. Really brilliant idea. So this is definitely that number theoretic question. No, this is different. This is probability permit to prove number theoretic question. And now you are completely, you see, you just give the definition of that, and now you have just to work on probability. Okay? Now you may say, what about 3 terms? 3 terms, then it starts to be something rather complicated. 3 terms is somewhat complicated because when you are looking at the different representations, you may have the same term. You see, if you are saying you have only representation by 2 numbers, it's quite clear that if you can write A is equal to E plus n minus A, and n is equal to A prime plus n minus A prime, if A is equal to A prime, then you have the same representation. Or if A is equal to n minus A prime, you have the same representation up to the order. Okay? So we are happy. If you have 3 terms, then it's a mess. Because if you have 3 terms, you have A plus B plus n minus A minus B. And n, if you have another representation, plus n minus A prime minus B prime. Well, it may well be that A is equal to E prime, but it's not the same representation because B need not be equal to B prime and those need not be equal to that. They just have the same sum, that's it. So it means that the event to be represented that way and represented that way are no longer independent. For 2 it is independent, it's very simple. So it took some time to know how to generalize it to larger number of summands. Although the question is quite natural, is to say, okay, instead of saying in the question of Sidon, you want the sum of 2 terms, every integer is represented as sum of 2 terms, but the number of representation is never too large. You can do it with 3 terms, the same questions. Okay, and this was in the 50s, and it was only in the 90s that this has been, the generalization has been done. Why? Because you have a question which is really an important question in probability about independence. And this is the difficulty, is that usually we are not working with questions which are really independent, they are almost independent. Okay? And we'll see that. So this is where one of the questions which is raised is the question of independence. When you have something which is not exactly independent but quasi-independent, how can you manage with that? You know Borel-Cantelli lemma. In any case, we are going to speak about that. If you don't know what it is, it's not a problem, but if you know what it is, it tells you in some way that if for independent random variables, then you are able to say that something occurs infinitely many times under some condition. Yes, but if they are not independent, what happens? Well, if they are almost independent, you can manage again. Okay? So this is the type of questions that you will have to work about. Okay? So about sums, what we are going to do is to work on something which is this model about squares or about cubes or about something like that. So you have, let us say, sum of s powers. We'll just end on that. You see, if you don't know how to do something in real life, you may say, okay, let us take a model and see what happens in the model, and maybe it will tell you something that goes on in the real life. So the last thing I want to tell, I'm definitely not going to go to this one. The last thing I want to tell you is sum of s powers. This is not very nice, but I should say sum of s integers, which are each sum of s powers. So in sum, what I am going to look at is to look at the set of n, such that n can be written as x1 to the s plus xs to the s. Number theory, all that are integers. Okay, x1 are non-negative integers, n is non-negative integers, and I want to look at this set. So the question was, does this set has a density? What can you say if you are looking at 1 over n and you count the cardinality of n up to n for which you have this? Does it have a limit? Does it have a lower limit? Well, what is the behavior when n tends to infinity? What can you say about sum of 3 cubes? Okay. What you say about sum of 2 squares, you know what to say. Landau already told you that this tends to 0. When s is equal to 2. Okay? This is Landau result. Possibly it was done before, but I don't know, I have no track of that. Because Landau is giving you much more precise thing. It tells you exactly that this number is equivalent to something which is constant divided by square root of log n. Okay? But now what about s larger than 2? We have no idea. Because when you make computation, you see something which is that this density seems to decay. But if it decays like log, like 1 over log, you see, before you can see something, you have to go very, very far. And with the means of computation you had in the 70s, there was no idea about that. Okay. So Erdős and Rényi made a model, exactly the model like that, except you will understand that instead of saying that the probability is 1 over 2 n to 1/2, the probability will be 1 over s n to the 1 minus 1 over s. Okay? So you can make this model, and it is this model. You have always the fact that this tends to a constant in the probabilistic model, let us say. So give their name, Erdős and Rényi. Model 1960, then we have always a positive limit. Well, okay, this is not that great because the only case we know the prediction, the probabilistic prediction is not correct. Okay, so about the sum of 3 cubes is not that great. Well, first of all, to prove that, to prove it, it's quite complicated. And if you look at Halberstam and Roth, which is from 1965, there's a chapter on probability methods. And they wanted to understand the paper of Erdős and Rényi, and they found that it was not that easy to follow, and they asked Rényi, who was still alive, he passed away in '69, who said, yes, there is a gap in the proof. Okay, so they could correct it, at least when n is equal to 2, for the same reason as before, that there is no question of quasi-independence. So, and in the book Sequences of Halberstam and Roth, then this is corrected at least for 2, and it gives a positive limit. Okay, so what we did with Henkar and Landreau in the turn of the century, we introduced indeed something which is to say, but you see here we don't use at all the fact that there is some distribution in arithmetic progression which is not even. Here you are just saying, okay, this is the number of squares. But for example, if an integer is congruent to 3 mod 4, it doesn't tell you that it is not a square, or if it is congruent to 2 mod 4. So you would like to plug in something which is a bit more arithmetic in that. Now, if you plug in some arithmetic in it, you can find something which is a model like that, in which you have a limit which is 0 for the square and which is positive for cubes and biquadrates and every other powers. And also at that time we had more means to compute, and we could find out that in the real case the density definitely seems to correspond to the probabilistic model. So it doesn't prove anything, the probabilistic model. It gives you some feeling that, well, possibly it should be the case, because we have a nice model which leads exactly to the same limit that what is observed in the real life. So it should be true, but of course it's not a proof. Yeah, so this is also another point about probabilistic model. It can be a way to explore situation. We are unable to prove anything, and for sum of 3 cubes, before we can say that it has a positive limit, I think, well, you have to go and read directly in the book that God is keeping, where Erdős is now reading that book, but it doesn't tell us much about that, unfortunately. Okay, so I think it's about 5, so thank you for your attention.